Gonna wait a couple more minutes, see if we get any more participants. We'll get started in probably 2 or 3 minutes. All right, guys, we're gonna go ahead and get started. To start, I wanted to mention some clerical things, really just planning for office hours this week. So Thursday, office hours are always Thursday, 6 to 8. However, I am going to have to adjust the time this week. And what I was planning on doing was holding an hour of office hours on Thursday from 6 to 7 p.m. And I want to preface this by saying that I will send out an email detailing everything that I say now. And instead of having that second hour on Thursday night, I was going to try and offer an hour on Friday morning, or it could be early afternoon, depending on what you guys would like to have held. So if you were planning on attending office hours between the hour after 7 and before 8, and there's a particular time Saturday that would work, or not Saturday, excuse me, Friday, that would work for you, shoot me an email. And again, I'll write you guys an email sort of explaining, but let me know if there's any particular time. I was thinking I could do that could be 9 to 10, 10 to 11, could be 12 to 1, somewhere in that realm. But again, if you can attend the 6 to 7 office hours, I will still be holding that at my normal link. I will get back to you on whether or not I'm able to open that office hours 6 to 8 p.m. link on Friday morning. I may have to send out an updated link, but again, more on that to come in my email, which I will send to you today after my second recitation. So we'll get started. Share my screen. Okay. So this week we will be discussing the chain rule and after that, implicit differentiation. So the chain rule is going to be the base. So the chain rule builds off of the skills that we discussed last week. And like I said, the course is going to get pretty cumulative from here on out. So we worked on the power rule, we worked on the product and quotient rule, and we worked on trigonometric derivatives, excuse me. And so we're going to use all of those today in the chain rule, which is just a composite of those. And then thereafter, we'll work on implicit differentiation, which is a more specialized type of problem. They're pretty easy to identify. And it works with the chain rule. And so once we get to those, we'll talk a little bit more about that. But to start, we're just going to work on the chain rule. Give me a second to lock my cat in the other room. Oh, here. Okay. So with these problems, when you start out, especially if you have a cube root, square root, something like that, you're going to have to do some manipulating ahead of time. And it's not all that difficult as long as you're familiar with translating between fractional powers and square roots, cube roots, whatever it is. So basically, since we know we're going to have to do the power rule on this because it's got a power, even though it's presented to us in a cube root, we're going to have to put it into its fractional power form. And now we're getting into the new topic, the topic of the chain rule. And in the chain rule and in other methods that we'll use going forward, we're going to call a certain part of the function u. So we're going to name what's within the parentheses here u. The reason why we choose this is because there are basically two aspects to this derivative. And this method can be applied to much more complicated derivatives with many more aspects to their derivatives, or much more complicated equations with more aspects to their derivatives. So the outermost aspect, and you see my note here says, or not here, you work your way from the outside in. You're going to start from the outside. It's almost like reverse PEMDAS. And we'll have a couple of examples that kind of show you the difference, specifically when it comes to trig and exponents. But we're going to call the inside here u because it itself has its own derivative. But we're still concerned with the power rule aspect of the derivative. The order in which we're going to take them is from the outside in. And so we're going to call this function, because this function has its own derivative, u prime, this function on the inside, we're going to call it u for the purposes of breaking it down and understanding it. When I do these problems and when I did that, so maybe my junior year of high school when I was taking Calc AB, I would use the U substitution method and think about it that way. Once you get a little bit more practice, some people don't even really need the practice. You can kind of just crank it out once you recognize the pattern. So up to you. Some of the examples I do use the U to represent a function within it if I think that it is a little bit better in terms of teaching, but you don't necessarily have to. You definitely won't get marked down points if you don't. So moving on. We're going to start by, so this is again just like a symbolic representation with the u substituted for this function here. So we're going to do the power rule first. We're going to drop the 1/3, subtract by 1 in the power, and we get -2/3. And then we multiply by the derivative itself. So that's the chain rule. The derivative is a chain and it builds off of itself. So we have the outermost derivative wherein we keep the function itself the same. And then we take the derivative of the function itself that's on the inside. So that looks like this. So like I said, the function stays exactly the same, but then we multiply it by the derivative on the inside. So this might be the greater aspect of the derivative. It takes up the most space on our page, certainly, but this is the core function. And so we have to account for its rate of change, for the rate of change of 4x. One doesn't have a rate of change. Technically, you could have done times parentheses 0 plus 4, and that would have been true still, but I did not do that. You wouldn't be expected to. And you also won't necessarily be expected to simplify it. I would award full points for this problem here, but I still did for just the purposes of working it out. Any questions on this one so far? We're going to do a ton of examples of the chain rule, and then we'll probably do 4 or 5 of implicit differentiation, which still works with the chain rule. But since this is the first problem, I do want to open up for questions. Does anyone have anything that they don't understand about the way that I did this?
So you would only, whenever you do u prime, you would only use the stuff inside the parentheses?
So yes, it's not always going to be just what's inside the parentheses, depending on the problem, but it's because this is a function, and then that function is also to the 1/3. So we take the derivative of the 1/3 because we're starting from the outside in of the 1/3 power, and then so we keep u the same, and then whatever's inside, whatever that first aspect of the derivative is being operated on, but not itself, we take the derivative of whatever's inside. So more often than not, yes, whatever is inside the parentheses is going to be u prime, and you're going to keep that the same as you do the outermost aspect of the derivative, and then it's just times u prime. Does that answer your question?
Yes, thank you.
Perfect. Anyone else? Okay, we'll move on. All right, so this one doesn't require any manipulation ahead of time, but it's going to be exactly the same as the last one. We're going to drop the 4 and reduce by 1 in the power, and we're going to keep everything on the inside the same for the first step. That's our first link in the chain. And then our second link in the chain will be to multiply by the derivative of the inside, which again, this is a constant, so it does not have a derivative. And we're going to do the power rule again on this aspect of the derivative on the inside, so it's going to become 6x squared. And I simplified it, but again, that's not necessary. So pretty similar to the last one, only this time we don't have to do any manipulation because it's not in a cube root or anything like that. It's in a workable form, and so we don't have to put it into a workable form. All right, so now a trig example. So first thing to recognize is that pi, it is also a constant, and in this case, it's the coefficient of x. So we're going to take the derivative of tangent of u when we assign u to be pi x. So that's going to look like secant squared of u times u prime. Because the derivative of tangent is secant squared, we're going to keep the u the inside, or keep the function the same on the inside as we do the outermost aspect of the function. In this case, the trig function is the outermost, and then the x variable is going to, and its coefficient are going to be the innermost. And so we get secant squared u times u prime. And then when we take u prime and we plug in for u, we get secant squared pi x, and then the derivative of pi x is pi in the same way that the derivative of 2x would be 2. And then if you wanted to, you could pop that pi out in front. That's what we're typically used to seeing. But again, I would award full credit for this problem, or for this formatting of this problem. So I just want to reiterate this whole outside to in thing. There will be an example when we get actually the next example. So I'll wait to touch on that. This example is pretty good for explaining that. Okay, so these two examples that we're going to do, this is number 6 from the book. I decided to throw this one in here because I felt it was good to contrast and to compare. But in this case, we see the power rule is on the inside. So the square root is affecting the x, it's affecting the variable. Here, the square root is affecting the entire function. And so it's going to look a little bit different in terms of what's on the outside and what's on the inside. So we're going to do some fractional power manipulation. We get sine of x to the 1/2, and we're going to call x in this case u. This is a type of problem that in my mind is a little bit more, there's not a lot of variables going on, so I wouldn't necessarily replace it as u, but again, you teach their own. So the way that it's going to shake out is we're going to drop that. So the 1/2 is not, getting ahead of myself. We'll get to that with the next problem. So it's going to be the derivative of sine, because sine is the outermost aspect of the derivative, which is going to be cosine of u to the 1/2, because we keep it, I think that is a mistake, but I believe I make a correction here. Should be cosine of u to the 1/2, because we're going to keep the function the same here. And then it's going to be times u prime. So we get, yeah, I made the correction here. So we get cosine of x to the 1/2 times the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. So in this case, the trig function, like in example 3, is the outermost aspect of the function. And we're going to start with the outermost and most often the biggest aspect of the function. I know that trig functions don't fall into PEMDAS, but it is going to be considered like what I call it the outermost aspect of the function, because I picture it as working your way into, specifically if you're working on a trig problem, what's on the inside of the parentheses, what is your variable. But that's not necessarily what the textbook is going to refer to it as. So to contrast, here, rather than having the square root over the variable, we have it over the entire function. And so we're going to do some fractional power manipulation, and we get that sine of x to the 1/2 is actually equal to the square root of sine x. And an important thing to note, because you will be given problems in this form, is that these two statements are equivalent. And if we're thinking about these problems in terms of working from the outside in for derivatives, then it's important to note that just because the 1/2 is technically on the inside of these other symbols, it's still the outermost, I don't want to say most important, but it's still the outermost aspect of the function. So just keep in mind that all 3 of these statements are equivalent. And just because the 1/2 is here rather than on the outside, because this is a little bit more obvious, you can think to yourself, okay, this is all the way on the outside, I'm going to work my way into the trig function. You just got to remember that this 1/2 means the exact same thing. Okay, so we're going to do the power rule on the entire function first and keep the sine of x the same. So we're going to drop the 1/2, and then we're going to reduce by 1 in the power, and then we will multiply by the derivative of sine x, which is just cosine x. Does anyone have any questions on the difference between 6 and this example that I threw up? If not, great, because this has been something that I've seen confuse some students. So if we're feeling good about it, that's awesome. But if not, feel free to ask. Otherwise, I'm going to move on. All right, number 7. This one is going to be more straightforward than the last. So you can probably guess we're going to start with the power rule outside in. We're going to drop the 4 and reduce by 3 in the numerator, or in the power, excuse me. And then we will do the derivative on the inside. And because it's a chain rule, it'll be the second chain. We'll just multiply it all together. And the derivative on the inside is going to be more of the power rule. We're going to drop the 6, reduce the power, and then we'll drop the 3, reduce the power. And this is a perfectly fine simplified answer. Okay, number 10. So like the last one, we're going to start with the fractional power. We're going to drop the 3/2 and reduce by 1. I feel like I might have made a mistake. Yeah, this is a mistake. So this should be 1/2. So 3/2, we're going to keep the inside the same, and then we'll take the derivative of the inside. So 2 is a constant, does not have a derivative. The sine, or the derivative of sine, should be cosine, but in this case, we have a coefficient of -1. And so the derivative is going to be negative cosine x. Number 11. So this one's going to require some fractional manipulation, but not much. It's only that you need to recognize that when you have something in the denominator, you can put its power, you can multiply its power by -1 and bring it up into the numerator, in the same way that inverses kind of pop whatever the term is on top or bottom when you add a negative to their power. And so we're going to do the power rule starting with -2. We'll drop that down front and reduce it by 1, keeping everything the same on the inside. And then we'll take the derivative of what's on the inside, and we will get negative sine t plus secant squared t, which I'll remind you guys, these are just the ones that I mentioned that you should start to memorize. So derivative of cosine is negative sine, derivative of tangent is secant squared. Keep that in mind, and also keep in mind that you can see any sort of variable in these with these trig identities, or these trig problems. Okay, so next one, f of x is 1 over the cube root of x squared minus 1. So you probably guessed we're going to do some fractional power manipulation. And so not only do we have a cube root, so it becomes a fractional power, but it's also in the denominator, and we want to bring it up into the numerator. And the reason we want to bring it up into the numerator is because we want the simplest form of this fractional power in order to do the power rule. We could technically keep it in the denominator and keep it as x squared minus 1 to the 1/3 in the denominator and do the quotient rule. But then that's just, like we discussed in last recitation, that's just adding extra steps for no reason, because the derivative of the top, when you multiply it with the bottom, would be a negligent term, because the derivative of the top would just be 0. And so we're going to put it all into one form, and we'll drop the 1/3 like we have before, reduce to 4/3, and multiply by the derivative of the inside, which is just 2x. Any questions? Okay. G of theta is equal to cosine squared theta. So I just rewrote it like that, getting you guys comfortable with interchanging between these forms. So it's just going to be, we're going to start with the power rule. We're going to drop the 2, and then it'll become 2 cosine of theta to the first. And then we'll multiply by the derivative of the inside, which is negative sine theta. And then I added in this little tidbit because if you guys are referring to the textbook, you might have seen that this is the most simplified version of the answer that they offer. And I put it in another color because I'm going to be speaking with Dr. Zalecki in our meeting tomorrow. And this is something that I was going to bring up to him, because if you were being tested on the chain rule and he asked you to do a problem like this, I would not expect him to expect you to have to use a trigonometric identity to give the most simple version of the answer after having done the calculus. I don't think that, what I'm saying is I think that this version of the answer would get full credit. I'm sure that this would too, but I don't think you'll be expected to do a problem like this and then have to use the trigonometric identity to find the most simplified version of the answer. But again, I put that in gray because I didn't want to not include the answer, and I didn't want to forget to mention that to Dr. Zalecki. And so more on that coming soon. So number 15, h of v is equal to v cubed times the square root of 1 plus v squared. And we are going to do some fractional power manipulation. So we're going to do now the product rule. We're going to get the derivative of the first times the second, which is 3v squared times the square root of 1 plus v squared, plus the first times the derivative of the second. And here we have to do the chain rule within the product rule. So we get We're going to drop the 1/2 power. We get 1/2 1 plus v squared to the negative 1/2. And then the derivative on the inside is going to be 2v. Again, we don't need the derivative of 1 because it's a constant. And all that multiplied together, and this would be an answer that I would award full credit for. If the problem we're asking simply just do the chain rule, find the derivative. So f of t equals t sine pi t. So this is similar to the tangent of pi x that we did before, but now we have another variable out front. So it's going to be another product rule example. We're going to do the derivative of the first times the second plus the first times the derivative of the second. Derivative of sine is cosine pi t. And then again, this variable on the inside, this is its coefficient. 3.14, whatever it ends up being, is going to be its coefficient. And so we multiply that because it also affects the greater rate of change. All right. F of x equals 2x minus 3 squared times x squared plus x plus 1 to the 5th. So looking at this, you can probably recognize that there is going to be some power rule involved in this and also going to be the product rule. So we're going to start with the derivative of the first, which is going to be the power rule. We're going to drop the 2. There should be another 2 right there. So it should be the derivative of the first. So we're going to drop the 2 and reduce by 1. But then we also have to take the derivative of the innermost aspect of the derivative, which I forgot to do. So this 2 corresponds to the dropping of the power, and this 2 corresponds to the derivative of 2x. And then multiplied by the second plus the first times the derivative of the second. So we drop the power, reduce it by 1, and then multiply by the derivative on the inside, 2x plus 1, and that's that. G of u is equal to u cubed minus 1 over u cubed plus 1 cubed. And this is one that I decided to represent with u. So we'll do the power rule, we'll get 3u squared and then multiply by the derivative on the inside. And then the derivative on the inside is going to end up being a quotient rule with power rule embedded in it. So we get 3u cubed minus 1, u cubed plus 1, and there's a squared here, times, and then this is the u prime. So this is the, I'm not going to use that terminology. This is the u prime. This is the derivative of the innermost aspect of the function. So we get the derivative of the first, 3u squared, times the second, minus the first, times the derivative of the second, over the second squared. Or if you're saying it in your head and you're using top and bottom, I apologize for throwing you off, but whatever you want to use, I still really recommend though that you use that you keep that kind of inner dialogue going and translating these problems to English, because otherwise it can get a little bit jumbled, especially when we get into these more complicated symbolic manipulations. So number 22, y is equal to x plus 1 over x to the 5th. So the fractional manipulation or fractional power manipulation here is just to put the x in the numerator, and so we're going to put it to the negative first. It's the inverse. 1 over x is the inverse x function, and so we're going to put it in its fractional form so that we can perform the power rule on it. So we're going to start with the power rule on the outermost aspect of the derivative, which will be the power rule with the power to the 5th, and we will drop the 5, reduce to 4, keep everything on the inside the same, and then multiply by the derivative on the inside once again. All right, h of theta is equal to tangent of theta squared sine theta. So outermost aspect is going to be the tangent, and then so we're going to take the derivative of tangent, keep the innermost aspect the same, and then we will multiply by the derivative of theta squared sine theta, which is going to be a product rule manipulation. And so we get secant squared of the inside, which is kept the same. This derivative of tangent is secant squared. Then we multiply by the derivative of the first, which is 2 theta times the second, plus the first times the derivative of the second. Okay. Another one, this one also requires fractional power manipulation. So we get t squared plus t cubed plus 1 to the negative 1/2, again, because square root translates to a 1/2, and then it being on the denominator can be remedied by putting it to the negative power. So we're going to do the product rule with the power rule inside of it. We will do the derivative of the first times the second plus the first times the derivative of the second. So this has the power rule and it has the chain rule. So I kind of want to point these out one more time so we can start to identify these. But this whole derivative uses the product rule. This is the first aspect, the derivative of the first times the second. This is the second aspect, the first times the derivative of the second. So within that, we are going to use the power rule to find this derivative here. And then we're also going to use the chain rule to find the derivative of what's on the inside. So those are the three aspects of the function. And that it's not always as simple as this, but it kind of looks to be that we have 1, 2, 3. I'm not saying that that's a rule of thumb that you should go looking and counting the terms and seeing how many aspects of the derivative or should correlate to the rules that you've learned, but it does kind of shake out that to be either the same amount or +1 of however many aspects of the derivative there are. That's how many, or however many aspects of the function there are. That's going to be pretty loosely, though, how many aspects of the derivative there are. So again, don't go fact checking yourself by counting the different rules that you used or anything like that. I'm just saying that you'll start to establish a little bit of a pattern. So now moving into implicit differentiation. I blew through this material way faster than I thought I was going to. Okay, so implicit differentiation. So when I had spoken with Dr. Zlecki last week, we were talking about our plan for the upcoming week. And so there are 3 topics that kind of go hand in hand. That's the chain rule, which obviously builds heavily off of the other differentiation techniques that we've already taught you. Then implicit differentiation, which is, I would say, an application problem, but it's still pretty heavily symbolic. And then there will be the story problems that we do, related rates. Those are the actual application problems that Dr. Zlecki, when we were in our meeting, I said to him that I would prefer that if we did the chain rule and implicit differentiation for this week, and next week worked on those story problems, because the story problems take a lot more thinking and working through in order to determine which variables are which, and those tend to trip students up a little bit. And so I wanted to spend time to focus on these today. But do bear in mind that this is not where the chain rule stops. We will do more complicated problems starting next. I'm sure that Dr. Zlecki will, if he hasn't yet already introduced them to you, he will introduce them this week, and then we will go over them next week in recitation. So I'll remind you guys that dy dx just means y prime when a function is when a function is written with x as its variable. Give me a second to drink some water. Sorry about that. Okay, so I put, excuse me, this -4x in parentheses because, let me backtrack. Okay, so implicit differentiation, it's pretty easy to identify these problems because you're not used to seeing functions, at least in this class, given to you in any other way other than y or g of x or something equal to, and then the function. But here it is with a variable or with a constant on the right-hand side. We'll also do problems that have variables that have other aspects of the function on the right-hand side and the left-hand side of the equal sign. And so this should be your dead giveaway that you're going to be doing an implicit differentiation problem. However, it is my experience that professors will often ask you explicitly to use implicit differentiation. And so these types of problems, if you can get down how to work through the symbolic manipulation. I know I say this about a handful of problems. I've said it already about a handful of problems, but these are the types of problems that I would hope that you would get full credit on every time, because with a little bit of practice, they're going to be exactly the same every time. As long as you've got those those skills that we've talked about so far: power rule, product rule, quotient rule, and chain rule, and then the trig derivatives. As long as you've got those down, it's just applying them to different scenarios. And so in this case, dy dx means that y is a function and x is a variable. So y has its own rate of change. And this is important because we've just discussed the chain rule. And so when a function has its own rate of change, like for example, 1 plus 4x has its own rate of change, we have to include that in our greater derivative. And so that is why I put parentheses around this -4x, because I want to treat that as the coefficient of y, because relative to x, y is, I mean, they're both variables, but y is also a function and it has its own derivative, and we'll see what that looks like in a second. So what I'm saying here basically is that x squared plus -4xy, those are equivalent statements, but I've grouped this because it makes it easier for when I'm doing the product rule, because we will do the product rule. Typically, we just do product rule between two aspects of a function that have the same variable. So it could be 2x times cosine of x, and then we would do the product rule between those. But implicit differentiation is different because we have the variable and the function in the same equation, in the same, I don't know, maybe string of math. I'm not really sure what the quite word is to describe it, but we do have to treat, so we treat x just as a variable, and we differentiate it normally as we have already with the chain rule. We treat y as a variable and as a function, and we'll see what that looks like now. So we're going to take the derivative of the first aspect. It's just 2x like we've seen in the past. Now we're going to do the power rule or the product rule on this part of the function, and it's going to be the derivative of the first, which is going to be -4 times the second, so -4y, plus the first, -4x, times the derivative of the second, which is just y prime. So I guess I'll give you guys a second to let this soak in if you guys aren't yet familiar with implicit differentiation, but this is what it boils down to, and it's exactly the same as what we would have done with variables in the past. However, instead of maybe simplifying the, say if y was tangent of x, we would not write tangent of x prime, we would write secant squared of x. But we're not working in those terms, we're working in terms of variable and function. And so we have to recognize that since it is a function, it has its own rate of change. So when we do the product rule and we find the derivative of the first times the second plus the first times the derivative of the second, since the second is a function, its derivative is not just going to be its coefficient, like with -4x, like in this case, it's going to be a whole new symbol, or not new, but it's going to be a symbolic representation of that derivative, which we will use to find, like we've been asked, to find dy dx by isolating that y prime. And so then with y squared, we're going to first treat it like a variable. So it's going to be 2y to the first, but then again, it has its own derivative embedded in it. And so it's 2y times y prime. And then since that's just a constant, its derivative is equal to 0. And so what we're going to do going forward is, and this is going to be exactly the same every time, you're going to take the derivative implicitly. So you're going to have y's and y primes and x's intermingled. And then you're going to isolate y. So you're going to get, or y primes, so you're going to get all y prime terms. I always do it on the left-hand side of the equal sign, and then all terms that do not have a y prime in it to the right side. And so looks like that. We get -4xy prime plus 2y prime, and then all this on the right-hand side. And then again, every single time, you're going to factor out the y prime, and it just looks like that, y prime times -4x plus 2y. And then you're going to divide this term from both sides in order to get y prime by itself. And then just a little reminder that dy dx, so this is the derivative of the function y with respect to the variable x. So that tracks with everything that I've explained thus far. And this is what's going to be equal to that. So taking a step back and thinking conceptually what that means that if I asked you to find y prime of 1 where x is equal to 1, you could plug in 1 here and it would give you the derivative. However, you would have to also have the original function in order to find what y value corresponds to that x value. So this is typical in the sense that we found y prime, and we can then use this equation to find the derivative at any instant on the function. However, we are going to have to do an extra step in order to find out what this y is before we find whether it's an integer or fraction, whatever, before we find the simplest derivative, because it's not just in terms of x anymore, it's in terms of x and y. Any questions on that first implicit differentiation example? Okay. Next one. This one's probably equally as hard. So, but I still, these aren't all that difficult, I don't think, if you understand the background. Maybe at first a little bit overwhelming, but I think that these steps should hopefully kind of give you some guidance. So this is the explanation. This is why we're doing it the way that we're doing it in terms of implicit differentiation. First step is identifying that it's implicit differentiation, but these problems kind of just scream that at you because we're not used to seeing the function being anything other than y equals g of x equals, and then the variables. So it's the fact that we have these mixed up x's and y's, and that we have stuff on both sides of the equal sign should tell to you that we're doing an implicit differentiation problem. This is the concept behind that. We're taking the derivative of y, the function, with respect to x, and so we have to include its y prime. We find all the y primes, get them on the same side, factor out all the nonsense that we don't need, because we want to find dy dx. That's the whole point, and dy dx is equal to y prime. Get rid of all of that, put it on the right-hand side, and voila, you've got y prime. So number 6 is going to be the same thing. We're going to do the power rule on 2x squared. It's going to be 4x. Now we're going to do the product rule on x and y. So we'll get the derivative of the first times the second plus the first times the derivative of the second, typical to what we've been seeing. Now we're going to do, and this is very similar to the last problem, except now we have a negative sign. It's going to be negative 2y times y prime. So we treat y first as a variable, and then we treat it as a function because it is both in this case. And then 2, its derivative is 0 because it's a constant. Then we are going to isolate y prime on the left side, or you can choose to do it on the right. We're going to isolate our y prime and then factor out first and then divide. I think I kind of combined steps here. Yeah. So I skipped a step. It should be xy prime minus 2y y prime, which then simplifies to this term. But this should still be here. This is still equal to this. And then the next term would be y prime, or the next line in the simplification would be y prime equal to this. So these two things, excuse me, these two are equal, and then y prime is equal to this. This is your final answer. So I'm making a note to fix that for next recitation. All right, so x to the fourth is going to be just a variable, so 4x cubed. Now we're going to do the product rule again. We get x squared plus y squared, which derivative of the first is going to be 2x. Derivative, or times the second, so we're not going to take the derivative in this case, I misspoke. So derivative of the first times the second plus the first times the derivative of the second. And this is going to be something that you just kind of like whip out and you don't even think about the more that you do these problems, because y squared is always going to be 2y prime. And so this will become something that you see pretty often. And then we do it for y cubed, which same situation. We drop the 3, reduce the power, and multiply by the derivative, treat it as a variable first and then as a function. And then on the right-hand side of the equal sign, we have 5 and its derivative is 0. And so our next step is going to be to isolate all the y primes. So we get all the y primes on the left, all of the non-y prime terms on the right. And so we're then going to factor everything out that is not a y prime. Well, we will factor a y prime out and leave everything else behind. And I did the same sort of thing that I did with the last problem, where I combined 2 steps. This is not a true statement. These are not true. These are not equivalent statements. Y prime, this term here is equivalent to this, and then y prime is equivalent to this. But I'm not sure what exactly happened, but I made a mistake in that. So when I send you out the recitation note this evening, the updated note will reflect the correct equivalent statements. All right, a couple more examples. A couple of trig examples. I don't think we've done one so far. Nope. So first, we're going to start with the product rule. And then we also make note of the fact that the coefficient, or I guess it's not a constant, but the coefficient of cosine of x is also a function. So that's going to change the way that we do this. Not really. Derivative of the first times the second plus the first times the derivative of the second, remembering that the derivative of cosine is negative sine x. Then it's going to be, you can probably just picture this without even thinking about it. It's going to be 2x plus 2y y prime. And then we will get all the y primes on one side. We will factor out. And we will divide. And I did this one properly. I hope you guys can see the difference between what I did incorrectly here and what I did correctly here. But same methodology, even with trig, it's just breaking it down into its distinct parts. If it's chain rule, it's starting from the outside in. If it's product rule, it's isolating which is the quote unquote first, which is the second. And I do want to make mention again of the fact that if you have a constant out in front of an x and a y, you could technically put the y with the 4, and you could treat 4 as a part of the derivative of y. I just think it shakes out to be simpler because the derivative of the simple variable x, in this case, negative 4x, is just going to be negative 4. But again, these problems are really just breaking it down into their parts and plugging and chugging using the skills that you've learned so far. And so now we've got one more example. we get y sine of x squared equals x sine of y squared. So derivative of the first times the second plus the first times the derivative of the second, which, so we have a chain rule embedded in here. There's not really much more explanation at this point because we've gone over the chain rule in depth at this point, but derivative of the first times the second plus the first times the derivative of the second, which has two aspects because the innermost aspect of the function is also a function with its own independent rate of change. And then we get the derivative of the first times the second plus the first times the derivative of the second, which has the chain rule and implicit differentiation in it. So then we're going to isolate all of our y primes on the left and all of our non-y prime terms on the right. Factor out a y prime, and then I did that thing again where I combined steps. But this term here is equal to this, and y prime dy dx is equal to this. Because, like I said before, we take the derivative implicitly. We differentiate implicitly. That's the first step. Then we isolate the y primes. Then we factor out the y prime. And then we divide to get y prime by itself to find dy dx, because that's what these problems are asking us to do. And that is the last example I have for you guys. I'll open it up for questions. Does anyone have anything that they'd like to ask? No? Okay, well, we're finishing up a few minutes early today. I will hang behind for a few minutes to see if anybody has any questions they'd like to ask separately. Otherwise, you guys are free to go. And I'll remind you guys that office hours will be from 6 to 7 tomorrow, and I'll shoot you an email asking for preferable times to make up that extra hour Friday morning or early afternoon. So hopefully I see you guys either tomorrow or Friday, and if not, I will see you next Tuesday.
I have a question. Is there a way for us to see what we did wrong on the quiz or
Which
the
quiz?
test? The one we just took.
The exam?
Yeah, the exam, sorry.
Oh, so legally you are allowed to ask we must disclose any information that you want to know about any sort of grading, anything like that. So the simple answer is yes. However, I don't know, I'm pretty sure that Dr. Zalecki did it the same way that I did. But when I graded the first half of the exam, the multiple choice and then a couple of free response ones, it was kind of a credit, no credit situation, except for the very first problem. And we did not write on your exams. I did not write on your exams. It was just, we broke it down into a spreadsheet. Each problem, you either got credit or you did not. So for my part of the exam, there's not really anything for you to see. If you lost questions on the very first question, then I could look at that with you and explain to you why I took points away on that. For the second half of the exam, Dr. Zalecki graded that, and you would have to speak with him, but he would certainly walk you through why you lost points. That is definitely something that he would do.
How would I even see where I lost my points?
So if you are, so you mean the spreadsheet that we have, you would like to see specifically which questions you lost points on?
Yeah.
Yeah, okay. So like I said, I'm not going to be able to give you much direction on why you, well, yeah, okay. So why don't we touch base? Why don't you shoot me an email and I can look at the records and I can let you know which problems you lost points on. And then you take a look at that and let me know which problems you are still confused about. And then from there, I'll help you with the ones that I graded, and I will let you know which ones Dr. Zalecki graded, so you can seek out help from him.
Okay. Oh, wait. I see the solutions. I can just...
Oh, you do? But you probably still need to know which questions you lost points on in order to check those, right?
Well, I can just look at my solutions, what I got, and just compare them, I guess.
Okay. Perfect. Well, let me know if you need any help with that.
Thank you.
Yeah. Any questions, Hannah? You're the last one with me. Mhm.